Hello and welcome to Firebird Tech. My name is Nick, as always. Today's project is more or less a personal project announcement about making my own DSO, digital storage oscilloscope. I've bought myself a bitscope. I've played around with oscilloscopes for a long time, but never really understood how they work. Now I am studying electrical engineering at university, so I am actually doing a bachelor's degree in electronics and electrical engineering. And this is more or less a personal project. It has no connections. It doesn't bear like anything on my uni degree. It's a personal project that I've wanted to do for quite some time. Because frankly, this thing, waveform update rate is atrocious. So some of the stuff I'll be using in this project will be stuff like ADCs, op-amps, analog to digital converters, operational amplifiers, differential amplifiers, microcontrollers, FPGAs, all this sort of stuff. So quite a lot of microprocessing, quite a lot of silicon will be used in this project. Other things that will be covered will be stuff like power supplies and stuff like that. So I'll simplify that. So the four areas that are going to be covered for this project, which won't just be 4 videos, it'll be quite a series of videos as I develop the project. The first probably video will be about the power supply, and a whole probably half-an-hour video just on the power supply alone. So this is how we turn mains input into a split rail and a fixed rail, so pretty much 3 differential rails. So plus or minus 15 volt, plus or minus, positive 5 volt, that sort of stuff. How do we turn 240 volts into that? That'll be probably a whole video by itself, half-an-hour video about designing your own power supply for op-amps and microcontrollers, that sort of stuff. Next video, or next part of it, next section, will be signal acquisition. So the front end, quote unquote, that most people consider on these, or any scope, is the front end. So taking a signal in and getting it to something that can be processed. That's the front end, or data acquisition. So there'll be a whole thing about that. So using operational amplifiers, differential amplifiers, all of that, and powering that, and doing all that stuff. Which will include how to use an analog to digital converter and all that stuff as well. So that will all be in that section. The next section is signal processing, so i.e. taking that signal you get from the front end and turning it into something meaningful, or changing the signal, or using that signal to do something with it. Most times that's where your big chunk of your ADC is usually, or sometimes the ADC or analog to digital converter can be on the front end. It can be either. So anyway, so that's digital processing. So that's turning what you get from the outside world into something that's actually kind of usable and processable, and you can do math on that, and that's where a lot of the math processors for stuff like Tektronix and Agilent scopes is in that chip. And that is usually done by an ASIC, or Application Specific Integrated Circuit, which pretty much is a chip that's designed to do that and that alone. You can't take that chip out and put it into another project and reuse it. It is an oscilloscope processing chip, that's all it does. So what I'll do is I'll build my own, but I'll use an FPGA, like the Spartan 6 LX9 I have here, which is a pretty mid-range FPGA, to be honest. It's pretty good though. And I have the Pablo Platform Logistar MegaWing V1.2 here, which has kind of like a 7/7 display. It's got the VG output, it's got an audio output / audio input. You've got joystick and an ADC, which is a good one, a very good ADC on this, analog to digital converter. So yeah, so that's part 3, is that digital processing, which I'll emulate with that, or create my own. And now part 4 is display, displaying that signal out to the world. So therefore, when you plug a signal in, your eyes can see that signal and interpret that. For something like the bitscope, the display is actually done. The display and the digital processing on this is actually done by a computer, which limits you to the interface which is on the back. In this case, it's 100 meg Ethernet, which frankly isn't enough. But that's the main bottleneck in this product is that interface. You're limited by that, so you're limited to about 50,000 waveform updates per second that this thing is limited to because of that interface. So that's why I want to make it an internal display, which is where this comes in handy. I want a direct display straight out to VGA, so pretty much you plug any VGA monitor into it, or D-sub, people call it D-sub, but it's the blue connector. So yeah, that's what I want it to go out to, so I can plug in any monitor, like any of the three behind me, and have an oscilloscope that's bam straight there, so we don't have bottlenecks and stuff like that from this interface. So yeah, that's the 4 sections: power supply, front end / data acquisition. We have data processing, or the brains. Then we have display or output, as most people call it. So that's the 4 sections that we covered during the process of this video, or video series. This will more likely be a video series. So we'll open up the bit scope and we'll go through what's actually inside this thing for your $800, and where most of the bottlenecks and why this thing really is a bit slow. So yeah, we'll pull this thing apart on the bench and have a look at what's actually inside this thing for your $800. So yes, another 10 out on this page. So enough about me rambling. I'll show you what other gear I've got. I'll explain a bit more by probably in the conclusion to this video why I've actually got an Arduino on the board in this pile of equipment as well. So enough about me rambling. We'll get on the bench. We'll have a look inside this and compare it to what I have here as well. So let's go. Right here then. As I said, we would go through the equipment that I have for this project. First, from on the right, just a pretty standard Arduino Mega 2560. This would be used for, let's say, an additional project part. I was actually planning to use this as a signal generator via like a serial communication bus. So from this, you'd tie a communication bus from your FPGA to this, and then from this would then produce like a 16-bit this would be a 16-bit digital to analog converter. But that's like really extra, but I thought I'd mention that as a brief thing. So yeah, next is this. Oops, sorry. Which we'll zoom in on so you guys can see what I'm talking about, and you focus the camera as usual. So what we have here is the Pablo Pro LX9. So this is a Pablo Pro platform. Ooh, I'm way out of focus. Give me a second, guys. So yeah, this is the Pablo platform LX9. Pablo platform. Pablo Pro LX9. That's a mouthful. This actually has on it a Spartan 6. I don't know if you guys can see that. Hang on, maybe I'll get a better view of this. Sorry guys. So this has on it a Spartan 6, as you can see, a Xilinx Spartan 6 XC6SL LX9. So pretty nice sort of mid-range to high-range FPGA. It's got like 36 input channels. It's got more than enough power pickups. It is powered off USB, which is a nice little touch. It's got the dual input output stuff there. It's even got a JTAG header, for crying out loud. This FPGA runs at 32 megahertz, as we'll look at in the bit scope, which is just off frame here. It only runs at like 16 megahertz, so it's like double the frequency, which means I can have double the data acquisition rate, which we'll talk about more when we get into that side of the project. So the other little board, where are we? Here we go. And we'll make that a little bit wider. The other little board we have is the Pablo platform Logistart MegaWing version 1.2. This has got a lot of helpful stuff on it actually. It's got switches, which I can probably use as like range switches. It's got a little joystick which I can probably program into be like menu, like scrolling around menus. It's got a 8-channel, I believe, yeah, 8-channel analog to digital converter, which I believe is a 10-bit analog to digital converter. I'm not 100% sure. No, I'll probably put it on like the bottom of the screen here what it actually is. So yeah, I think it's a 10-bit, but it could be 8, it could be 12, I can't remember. Other thing it's got on it, which is really handy for this project, I was mentioning in the intro, is it has a direct, what is called VGA, or sometimes called D-sub, connector straight on the board itself, which means I can plug that straight into a monitor, and boom, I have my output No worrying about fussing about custom built software for computers and that sort of stuff. It also has like a little audio jack as well, which I may or may not use. I don't 100% know yet. Another thing it has is an 8-segment display, a quad 8-segment display. Again, probably something else I'm not going to end up using, but who knows at this stage. So yeah, who knows. So that's got most of what I need. So without further ado, put that off the side and bring the main attraction into view. This is the Bitscope. Pacific model, I believe, is the Bitscope. I'll just show you the label. It's the Bitscope DS326N0, which is the Internet capable. It's got the 1 megabit of memory in it, so it's pretty nice. It is powered off 12 volts, which is kind of interesting. And we'll see how they get their split rail for op amps in there inside as well. So pretty standard thoroughfare. 2 BNCs, channel A, channel B. You've got the one of the ways to get the waveform generator out, because this does have a signal gen in it, but it's so useless it isn't even funny. External trigger, external ground, sorry, and also the digital input. So this does actually have a logic analyzer in it, but I can make this into a logic analyzer very, very quickly. So I can put the FPGA and make it a 16-channel logic analyzer if I want. So yeah, and we've got our LEDs to show what we've got. So let's tear this thing apart, shall we? You are so not going to focus. So, lucky enough, Bitscope was thankful enough, and all it takes is just 2 screws to undo this thing. It's really simple to undo and pull apart if something breaks inside them or something like that. So I'll give them credit for that, and the ridiculously robust housing. It's actually a photo up on their website of one of these getting run over by a forklift, and it still worked. So I'll give them credit for the good build quality. As you can see, it's fairly densely packed actually. So it's fairly densely packed. So this is their front end that I was talking about in the intro. This is what I'm going to try to build myself. So this is all the front end. This is got your amps, op amps, all that to bring up the signal level and all that. Back here we see our signal memory. This is our storage before it goes into the DSP, or digital signal processor. So this is 1 megabit, which is quite a lot. So we have a little lattice. I'll try to get a better view of this without the light being an issue. There we go. So we have a lattice DSP in there, and its firmware, so 36N is in there, so that's its firmware. So that's its flash, so it contains like all the menus, what it actually needs to do and everything. Its pin allocations, all that, so that's a little DSP in there. Here we have all our stuff for our pod connection at the front, which contains all of our digital signal, 8-channel logic analyzer, our probe A, probe B, voltage stuff, handy stuff. And then we have our network controller. Where are we? Network controller here with its actual Realtek network controller, which is nice to see a hardware implementation of this, not trying to do it off the DSP. And then we have, there we go. Then we have the power supply. So we've got our main power input here, all our power filtering here, protection diode, a couple of linear voltage regs here. We've got all our voltage capacitors here, inductors, big fat 7805 to 4 or 5 volt logic in this thing. Then we have our little voltage inverter. This is how they turn a positive voltage from here into a negative rail for the op amps over here in the front end. So yeah, and there's absolutely nothing on the back before someone asks. So yeah, that's what the Bitscope is. Most people will say, well, why isn't this good enough? And the big question and the big thing with this is why it's not good enough is the data acquisition rate is hopelessly slow. Even when you crank this thing up to full, you're still talking less than 50,000 waveform updates per second, which is slow. So it can't capture glitches, it can't capture much of anything that's actually realistically useful. Yeah, it's okay for like DC measurements, it's good as like a precision voltmeter pretty much. a voltage meter. Yeah, it's okay for looking at like main signals, but as soon as you go over like 100 Hz, it starts to glitch out and it can't capture waveforms. So, yeah, again, it does what it does, but it doesn't do it well enough. Realistically, for the money, you should really just go buy yourself a Rigol, I think it's DS1026 or something like that, which is way better than this. It even has high waveform update rates, it's direct output straight to a display and all this other stuff, so yeah, nah, probably wasting my money, personally, but that's my personal preference. So what we're going to try to do is fit this and make this. This is what I'm going to try to create. But instead of it going out to an Ethernet jack, it's going to go out to VGA. So that's a little project as we go. So I'll put this thing back together, we'll go back to the talk view, and we'll go over sort of what we'll go through in the sort of next week and stuff. A bit of a conclusion and a wrap up. So let's go. Okay, conclusion time, or wrap up time. So we had a look at what's inside one of these, the Bitscope, my personal opinions on these things. For $800, they're not a really good buy personally. You can buy yourself a really decent 2-channel a good like Rigol DSP for the same money. Yeah, not as portable. Yeah, you can't just chuck them in your bag and take them to uni or take them to work. But really, the performance this thing gives is so under par that I'd actually prefer to carry around a Rigol big fat actual oscilloscope than this. So yeah, so most of what's on there, except for like the op amps and the power supply, can actually be emulated by this, but by an FPGA, which is good. Don't get me wrong, this thing's pretty much boss. So there'll be tutorials as well on how like use VHDL on the channel as well. So there'll be a video series as I learned VHDL, which is how you program these. So where you program this by C or C++ through the Arduino IDE, you program this through the Xilinx IDE, but you use VHDL, which is a totally different ballgame. Yeah, you can program this thing in C, but VHDL has a lot more power to it. A lot more power. So yeah, way more powerful than VHDL. So that's another reason why I have this out. So yeah, the lattice DSP on this will be replaced by this big chunk of awesomeness that is an FPGA. For those who do want to know what a DSP actually means, it's a digital signal processor. So it pretty much has digital to analog coming in one side. It has an FPGA in the center, a very small one, probably about a third of what the size of this one is. And then it has analog to digital on the other side, or digital to analog on the other side. So it can create sort of analog to digital, digital to analog signals very easily. You usually see them in sound cards and computers, because they can take an analog signal and turn it to a digital, and then pump out do some signal processing on that, and then turn that out to a digital signal. Usually codecs are usually stored on these, like MP3 codecs, that sort of thing, or automatically stored on these. So yeah. Anyway, enough about me rambling. So the project will be to create one of these for less than $800. That is, in my opinion, more useful, has a higher waveform update rate and those sorts of things. Less bulky, that sort of thing. So I do want it to be smaller than this, but it will direct plug out straight to VGA, so there's no sort of bandwidth limitations on this. So there'll probably be like a control thing on the top, like a control interface, probably built on top of this. So we'll have like a joystick and probably a couple of switches, that sort of thing, probably turning channels off and on, or stuff like AC coupling, DC coupling will probably be controlled via these switches on the front, but those sorts of things. I don't expect to use the 7-segment display, but if you've got an interesting suggestion for what I should use a 7-segment display for in an oscilloscope, then leave it in the comments below. I'd be interested to see what people think about what I should use a 7-segment display for. But yeah, the other great thing about this is it's Arduino compatible. This whole like Mega Wing board is Arduino compatible. So I can learn how to program the SPI enabled, so serial output enabled analog to digital converter that's on this board on the Arduino, and then transfer that knowledge over to the actual FPGA, which is really cool, like super awesome, which is really cool. So that's where that comes into play. So yeah. So enough about me rambling. So if you like this video, like it, dislike, that sort of stuff. If you dislike the video, give me some positive criticism on what I should change. I know I should stop rambling, but that's just me. So like, dislike, share, comment, rate, all that stuff. So yeah, enough about me rambling. So thanks for watching Firebird Tech. Hope to see you in the next one. One last note before you guys tune out. I am currently in exam period, so the videos are probably going to get like less and less frequent. I may not do a video every single week. So enough about me rambling. Thanks for watching.